Hi, in this video, we're going to talk about histogram-based gradient boosting. Okay, so in classic gradient boosting, what we're going to do is we're going to take an ensemble model of decision trees. And how we're going to proceed is that we're going to create a bunch of decision trees that individually are too short, but they're going to work together to correct the errors of the previous trees to get a better fitting model. So each individual tree is a weak learner, but the ensemble is very powerful. Where I work, this is by far the most popular way to fit a model. By far, hands down, my coworkers love this. And I've been working on projects, and for regular old gradient boosting, does decent job. I feel like random forest is my preferred way to go, but I can't tell them that they're wrong. Now, something that has been happening kind of regularly at work is that histogram-based gradient boosting models have been slightly outperforming random forest and gradient boosting models on my personal projects. And so I feel like this is something worth sharing, worth talking about, because I'm getting more accuracy out of my models. And, these look like they're pretty good to me. I haven't launched one into production yet, but I could definitely see the potential for it. How this is different than regular old gradient boosting machine GBM is that in histogram-based gradient boosting is that it's going to bin our numeric predictor variables, kind of like in the bins that we use for our histogram. That's why we have the name histogram-based gradient boosting. What does that do for us? Well, it makes it so that we have fewer breaks in the numeric variables to try and split on so it can be faster. Now, potentially, we could lose some accuracy because we could miss the optimal splits. But from my experience from looking at this, it's doing a pretty good job. And so I have to say it's definitely worth, that risk, because we get a time savings, because it's fast and quick, which is super important to me. And, the accuracy has been better than regular old GBM and random forest, not by a heck of a lot, but it's been consistent for my personal experience. So I think that this is definitely one that we want to have in our tool belt. Now, another thing that I really love about this, the implementation in scikit-learn, is that this will handle missing values for you. All right, so that's huge. I don't have to deal with missing values, and I don't have to do as much data prep, because if I have a numeric predictor variable, what's going to end up happening is that any monotonic transformation, any transformation that preserves the original order between observations of greater than or less than, anything that preserves the order, any transformation isn't going to improve model performance whenever I'm using a tree model. And so that means that this requires very little data prep. All right, so I've been in the experience where I'm in a meeting, and stakeholder asks a question, wants to know something. I've got the data. I'll load the data, and if I can, get a quick model going to give some kind of informative conversation about this. And this has been very good for my professional career. I'll say, hey, I just built a model that says this right then and there, and then that helps that helps set it up so my time is used efficiently. That way I don't have to come back and have a meeting with them later. And also, since I can produce results quickly, that gives my stakeholders more faith in me. So I like doing that. All right, so histogram-based gradient boosting is a modified version of gradient boosting machine, GBM, the classic gradient boosting model. And, it's optimized for both speed and scalability because of how it handles numeric variables by binning them in a histogram manner. Now, we can use this for regression and classification. Now, there are other situations that we can use it in, such as like, selection, or like for like recommendation engines, but I don't see that as a really strong feature in scikit-learn, so I didn't put it in the notes. So, this is an ensemble learning method where multiple weak learners usually decision trees, are combined to form a strong predictor overall. The histogram-based part refers to how the algorithm handles the numeric predictor variables by bending them into discrete intervals. And so what this does is that this reduces the computational complexity. Without this step, potentially at with a tree, when it takes a numeric predictor variable, it's going to go between every unique pair of every unique cutoff to find the optimal cutoff. And so if I had 1,000 distinct observations, that would be a 999 cuts to have to try. And so that's a lot. The histogram, it's just a fewer numbers to even try. All right, so instead of evaluating all possible split points for our numeric predictor variables, we're going to bend our continuous features into fixed number of discrete bends. And so this reduces the number of potential splits. And so this means it's faster for us to get things going. And this can handle large data sets better because it's not doing as many computations. And so, yeah, it's a huge advantage for large data sets, especially if we have a lot of numeric predictor variables. My experience with this is that even though we are really actually compromising like the fine-tuning aspect of finding splits, this is outperforming on my holdout set slightly better than the other models I'm building. It's been the best one several times on a couple of different projects. And so I'm seeing this as this is a good way to go. Now, the improvement over random forest and GBM wasn't great. It wasn't a huge amount, but it was better. And this has been a very consistent feature for me. Also, we can do parallelization pretty easily on this, making this easier. And I love it that this handles missing values for us, that I don't have to do that. All right, so let's talk about how this works. Whoops, I went down too far. All right, so we're going to start with an initial model, typically predicting the mean of the target variable. Then we're going to do an iterative process. We're going to compute the pseudo residuals, which are the differences between the observed values and the current predictions. We're going to fit a regression or classification tree to the pseudo residuals using the histogram-based binning approach, which at this point has already been computed for every single numeric predictor variable. And we're going to update the model by adding the prediction from the new tree scaled by the learning rate, or our shrinkage is another word for that. Then we're going to repeat this over and over and over until we get to our stopping criteria, which will frequently be the number of trees. Now, for regression, we're going to predict a continuous target variable. The algorithm fits a series of trees to the residuals of the predictions to minimize the loss function, which is typically the mean squared error. Most of the time, we're either going to be using mean squared error or mean absolute error. Mean squared error does a better job as a loss function to avoid big mistakes. And that's typically where we get burned as data scientists, is that we want to avoid big mistakes more than we want to reduce the overall error. Mean absolute error, conceptually, it sounds like it'd be the better one because it gets the average error down, but it doesn't do as good of a job as making sure we don't have any gross big mistakes in them. So I lean towards mean squared error unless I need to explain things to my stakeholders, because if they're ones that are kind of scared and nervous about things, mean absolute error is advantageous that I can just say average error. I don't have to say like square root of the average squared error or anything like that, like for mean squared error. Now for classification, we're going to be predicting a categorical target variable. The algorithm is going to fit a series of trees to the residuals of the predictions to minimize the loss function. And most of the time for this, we'll be using log loss. Now, histogram-based gradient boosting can be adapted for ranking tasks, where the goal is to order items according to some criteria. This is useful for information retrieval and recommendation systems. All right, so advantages to this approach: it's efficient. I mean, the training process is pretty quick. Also, we've got like less memory aspects going on just because we're simplifying our predictor variables for us, and this can handle large data sets better than GBM. And so, it's faster, handles larger data sets better, using less memory. And I have personally not experienced a loss in accuracy. So I'm thinking that this is the bee's knees. All right, so now implementation. For me, I've only used this with scikit-learn. I have not worked with light GBM. I have coworkers that have and recommend it. But so the hist gradient boosting regressor is for regression in scikit-learn. The hist gradient boosting classifier is for classification categorical target variables in scikit-learn. Now, this next part I copied and pasted from the help documentation. The histogram-based gradient boosting is much faster than gradient boosting for large data sets. So specifically when our sample size gets over 10,000. And histogram-based gradient boosting has native support for missing values. And this is how it handles missing values. So the tree grows learners at each split, whether samples with missing should go left or go right. So it takes a look when it has a missing value and makes a judgment call on should it go left or should it go right, as long as I have a missing value in my training data for that predictor variable. And so it makes a decision of left or right based off of the potential gain. Now, when predicting samples with missing values are assigned to the left or right with the way that it was handled with the training data. Now, let's say my predictor variable in the training data set did not have any missing values. Well, then what's going to end up happening is that it's just going to send the missing value in with the larger side of the split. And so wherever left or right, whichever one has more samples in it, that's where the missing values will go. I mean, it's not the best way to handle this, but without ever like seeing a missing value, what else is it going to do? And by knowing this, I can know that, hey, if I let missing values stay in my data set, this is what's going to happen. And I can make the decision to impute or not. But I like this feature, especially if I need like a real fast model, get some inference, get some understanding, and tell to my stakeholders, like in that meeting on Teams. That way I don't have to make another Teams meeting, because I don't know about you, but I hate meeting in Teams and on Zoom. And I'm in Zoom right now. All right, so now here's an example data set. So I'm going to go ahead and use a data set that has all numeric predictor variables. This is the California housing data set from 1990 US Census. And so here, the target variable is the median house value for California districts. And so this is going to be a regression task. I'm copy and pasting from scikit-learn the information here. Now, you'll notice that's California districts. So we're not looking at individual houses. We're looking at an area, geographic area of the homes. And so we've got median income of the households in the district. We have house age, the median house age in the district. We have the average rooms, in average number of rooms of a house in the district, average number of bedrooms in houses in the district, population in the district, the average household occupancy, and then we have latitude and longitude. Now, the latitude and longitude of this data set is highly correlated. I was really surprised by this aspect. So that's something that I'll show you in a moment, but that is something that would come up during my feature selection. Here, I'm not doing any feature selection. I'm just going to dump everything in. And I've got a surprise for you at the end, which I hope you find shocking. All right, so the median house value is our target variable. And we've got just over 20,000 observations and 8 features. All right, so to get this data set, we can use fetch California housing from scikit-learn. And, so here's the function to pull it. Notice I'm using this default data set. To be able to pull this data, I have to have an internet connection at the time. Not a big deal, but if you're working on an airplane or something like that, maybe a hotel with very poor internet connection, just know about it, deal with it. All right, so now to set up my data, I'm just going to use pandas just like I normally would. Here I'm calling the data and then I'm putting in the columns and then I'm setting up what the target is. Notice that the target variable of mean house value is not in the data set. So when you call this data as is, this data aspect does not include the target. Target is in the target slot. All right, so here's my data set. All right, so now these are all numeric. Something that I do when I'm building models is that I'll have my data organized by how I'm going to approach, data prep. I'll have my numerics, or maybe possibly counts, and like numerics are going to be anything that is numeric, maybe only continuous, maybe I'll discrete or counts or something like that will be another one. If I'm going to handle like ordinals in a certain way, I'll have a list ordinal and I'll have list categorical. They're all numeric, so it's just list numeric on this one. And so let's go ahead and take a look at what's going on. And so here I can see that I have the same count across the board. So either they all have the same number of missing values or no missing values. And here I can see what the averages are, the standard deviations, and the box plot numbers off of there. Now here, something that's more interesting to me is the histogram of these. And you'll notice that these are definitely not looking normally distributed. All right, so here's my target variable. And here's, each of these. And so I'm looking at this, definitely something going on, like, there's a few of these that have just a crazy large number compared to the others. And so I'm not really feeling this presentation of the data. So let's go ahead and do something to improve it. Now, I'm using tree-based models. So as long as the splits are okay, in the histogram, when we do the histogram binning, if the splits are good, then you know what? I don't really need to touch this. I can just run with it. But honestly, I'm not feeling, so I've got almost everything like close to zero. I've got almost everything close to zero on these. And so let's see if we can improve this using the power transform. I'm going to use Yo-Johnson, and then I'm going to center and scale the data to have mean 0, standard deviation 1. And I'm doing this to get a better histogram binning off of this. Now, also, I'm going to consider the correlation between the observations and my target variable. And let's go ahead and plot this. So here's the code to get the correlation, just, dataframe.core. And then I'm going to go through and I'm going to do a heat map to show which ones are correlated with each other. Now I'm going to go a little bit further and I'm going to go ahead and organize my heat map by variable clustering. I forgot to plot the dendrogram, but I should have done that also to make this, to give us another layer of interpretation. But when we look at this, you'll notice that latitude and longitude are highly correlated and they're negatively correlated. So I have an idea of of relatively how things are laid out, in relation to each other, north, south, east, and west, as we go from south to north. Overall, the trend will be to go. As we go from west to east, overall, we will be going southward because of this negative correlation. And that's a pretty strong correlation. Now, we also see a correlation between the average number of rooms, the average number of bedrooms. Okay, that's definitely, that's not surprising. Now we see our target variable has the strongest correlation with the median income. Then we have average occupancy, house age, and population also coming up. And now here, this is showing a little bit of a correlation between house age and population, but it's not that much. All right, so now, okay, so here on this step, I am partitioning my data. I'm going to choose to do a random split for my train validation and test split. And so I'm just doing NumPy's random choice on the partition ones. So training is the data that I build my data on. Validation is the one that I use to select my model or do parameter tuning depending on the model structure. And then test is my honest estimate of how the model will perform. If I'm building a lot of models, it can work out that just by fluke, by happenstance, a model looks really good on the test set when it's really not a good situation. By having two holdout data sets, I'm making sure that I'm not taking a risk on those random flukes. All right, and so now for my numeric predictor variables, I'm going to handle my outliers. So the ones that are more extreme than the 1% quantile or the 99th percent quantile, the ones that are very, very far to the left or very, very far to the right, I'm going to cap the values. This is kind of mild capping. I could have been a little bit more aggressive with it, but I think this will work out. Now, I'm going to use the power transform. By default, this is going to do Yo-Johnson transformation, similar to box cuts, but it allows negative values. And you know what? I honestly don't really see an advantage in most situations to use box Cox over Yo Johnson unless I'm very sure of the type of data that I will get in the future. So I prefer Yo Johnson. And then after that, I'm going to center and scale my data to have mean 0, standard deviation 1. And just to make sure I don't have any missing values, I'm going to put in a 0. So I'm using the mean to impute. Now let's go ahead and take a look at what I got now. All right, now look at this. Look at how much more beautiful this is. I mean, this looks pretty close to a bell shape. This looks closer. This looks closer to a bell shape, closer to bell shape. Like this is much improved. I feel much better about this. I feel better about the splits of the histogram because, you know, before I had like one huge, huge, huge bar, and then there were values that were so far to the right, I couldn't even see them on the histogram. I didn't like that split for the histogram binning. So this is a huge improvement on what's going on. Now I'm going to go through, I'm going to build my model. Now the learning rate is also the shrinking parameter. And this is by far the most important parameter for this type of model. And so I'm just going to go through a bunch of different values for this. So I'm going to create a list of learning rates. And, you know, it's just these guys. The default is going to be 0.1. And if I had 1, that would be no shrinkage whatsoever. So this is a multiplicative factor. The smaller the learning rate, the less impact future trees will have on the predictions. And so we can use this to prevent overfitting. So because of the gradient boosting method, I have a huge risk of overfitting. That's because what we're doing every time I build a tree, I'm looking at where are things going wrong. Let's build a tree to correct how it's going wrong. And so it can set it up so that on my training data set, if I don't have any shrinkage, it can go off the rails and overfit. So I don't want that. So let's go ahead and fit this. So here I'm creating a list of models. Notice that I'm not fitting anything. It's just, hey, this is what it is in each slot. Now I'm going to go through each one of these and I'm actually going to fit the model. I'm going to call it list underscore fit. Notice I'm doing the fit, passing my training data in. Looks very similar to the previous, but now I actually have fitted models in this list. And now I'm going to predict it on each of these. And I'm just going to take a quick look to see, do things look consistent? And I went ahead and named the columns by the learning rate. All right, so now let's go ahead and compute the mean squared error for our training, validation, and test statistics. And I'm going to go through, I'm going to sort by test, validation, and training. And you'll notice, hey, by the test statistic, I get the lowest mean squared error at 0.09. Now, I want you to notice something. My test statistic and my validation, they're looking pretty close, about 0.31 for my mean squared error. But look at my training statistic. That's 0.19. Over here, I've got, about 0.3. So over here, I've got 0.2, roughly speaking. Here, I've got 0.3. Whenever you have a gap between your training statistic and your holdout statistic, that's an indication of overfitting. If the training statistic looks much better than your holdout statistics, worry about overfitting. And if I scroll down, I can see it looks like I've got some overfitting going on. Now let's visualize this. Let's actually take a look at this. So I'm going to go through, I'm going to plot this here. I'm using Seaborn. And look at this. This is actually a beautiful example of overfitting. I have a bunch of overfitted models. Check out, like you can't even see it on this bar. Look at how low the training is. So here, the model made the training mean squared error disappear, practically speaking. It's super, super tiny. But when I look at the test statistic, it's up here. Like, I'm going to make this a little bit easier to see. Look at how high the test and validation mean squared error are compared to the training. And so this is an indication that I have severe, severe, severe overfitting. So the bigger the gap between the blue and the orange-green bars, then that's more of an indication of overfitting. So when I look at this, the one that has the least amount of overfitting is the one that had the largest, or the greatest shrinkage going on, the one with the lowest learning rate. And so look at that. So here, now I think that this indicates that there is overfitting, but my point of view is every model overfits. It's just some are useful. So here I've got overfitting, but it's not that severe. Here, the overfitting is worse. And now here, this is where I would definitely, like, I wouldn't, that's enough of a gap. I wouldn't want to use it. Now, another thing to point out is you'll notice that my best models in terms of the unseen data are in this range here. So my validation and my test statistics are all pretty good. So let's go ahead and say that 0.08 is the model that's looking the best to us. I mean, that's best on our holdout data, but we have an indication that we have overfitting. We have to the model is picking up features in the training data that's not in validation nor test. All right. So if I wanted truly the best performing model out of this list and I'm stuck with this list, there's nothing I can do about it, then I might want to go with 0.08. But I know that I have overfitting and I can get some wonkiness. You got to make a judgment call. Here, 0.01, it's like what I see is what I get. I know how my model is going to perform in production, but you can see that I didn't get the best accuracy that I could possibly get. In data science, all meaningful questions are subjective. Which one would you do? It depends. Honestly, I would talk to my stakeholders. I would talk to my boss. I would do whatever it takes to make people happy because that's how I get my annual bonus. And all right, now let's actually talk about methods to deal with this problem. All right, so how can we actually address this? Well, first and foremost, we can reduce the number of trees. I believe the default is 100. Well, if I cut that down to 75 or 50, maybe this overfitting problem would disappear. We can also reduce the tree depth. I don't think that's really going to do much on a weak learner, an ensemble tree model, but it's a tool in our tool belt. Maybe I could try that. Also, we could increase the shrinkage by reducing the learning rate. So you'll notice that my best model in terms of overfitting had the lowest learning rate. I could keep on shrinking that down. Also, the histogram gradient boosting has an L2 regularization option to it. The default is 0, meaning that there's no ridge regularization, but I could invoke that, and that might solve the problem for me. Now, the one that I use most often to solve overfitting with trees, and that's usually with random forest, is increase the minimum sample leaf. The default is 20 on histogram gradient boosting, and so maybe I want to increase that to 30. That would be my first guess. 30, just because that's a magic number in elementary statistics. I always like to have 30 as a number. Also, we could use cross-validation. That might solve the problem because there, if I'm doing tenfold, I'm using 90% of my total data, and that could prevent problems with the overfitting. Also, I could increase the training sample size. All right, so I took 1/3 of my data, put it into training, 1/3 into validation, 1/3 into test. Well, if I was to shrink that, and increase, maybe 70, 15, 15, maybe that would solve the problem. Also, we could do feature selection. So remember that from that heat map, I knew that latitude and longitude are highly correlated with each other, and average number of rooms, average number of bathrooms are highly correlated. I would like to go in and do feature selection. Something that's unfortunate about histogram-based gradient boosting is that it doesn't give us a feature importance. We have to go to other model techniques for that. So maybe I could go to another modeling technique, look at feature importance, and start removing predictor variables that have low feature importance in them. Also, we can invoke early stopping. All right, so we talked about histogram-based gradient boosting. I found that this is a powerful technique to do our supervised learning models. I've found that it's outperformed other models pretty consistently for me, not by a huge amount, but if it's consistently good, hey, let's keep on using it. Well, that's all I've got for you. Life is short. Do math.